All right, good afternoon, everyone, and welcome to the kickoff webinar for the Water Security Grand Challenge. My name is Heather Goach. I'm a fellow here at the U.S. Department of Energy and have helped organize this webinar series along with my colleague, Catherine Harshani at DOE. We are very excited to kick off this series. Today, you will hear about the Grand Challenge goals from each of the team leads, including the cross-cutting energy water desalination hub. And at the very end, we'll have an opportunity to ask questions. A few notes before we get started. This webinar will be recorded and may be posted on the DOE's website or used internally. So we ask that you send questions and to whom you are addressing the questions through the Q&A chat function of the WebEx. I will return to these questions at the end of the webinar for the team leads to address them. So with that, I will introduce Kevin Jane, one of the co-leaders of the Water Security Grand Challenge, who will introduce the webinar series.
Thank you for the introduction, Heather, and thank everyone who is joining this webinar. So I would like to get started by answering the question, what exactly is a grand challenge? And a grand challenge is a big, difficult problem that, if solved, would bring significant benefits to society. Grand challenges often include the following important characteristics. They feature a measurable endpoint that is highly ambitious but achievable, drive the need for collaboration between multiple disciplines, some of which do not normally interact, are too big to be undertaken by one or even a few organizations, and finally, they capture the imagination of the public, thereby facilitating strong support for the resources required to achieve the goals. Next slide, please. And the Water Security Grand Challenge is a White House-initiated, DOE-led effort using a coordinated suite of prize competitions, early-stage R&D, and other programs to make rapid progress, advancing transformational technology and innovation to meet the global need for safe, secure, and affordable water. And by 2030, we would like to launch desalination technologies that deliver cost-competitive clean water. Number 2, transform the energy sector's produced water from a waste to a resource. Number 3, achieve near-zero water impact for thermoelectric power plants and significantly lower freshwater use intensity within existing fleets. Number 4, double resource recovery from municipal wastewater. And finally, develop small modular energy water systems for urban, rural, tribal, national security, and disaster response settings. And I got a little ahead of myself, but I wanted to give a little context on how this came about. This was launched in October of 2018 by Secretary Rick Perry, and several hours after the launch, we held a workshop at DOE's National Renewable Energy Laboratory, and we gathered input from external experts to inform the development of prize competitions that DOE could launch to support the Grand Challenge. Next slide, please. After the workshop, DOE recruited interagency participants, agencies including EPA, DOD, DOI, USDA, and FEMA, to join cross-functional teams aligned with each of the Grand Challenge goals. And each team is identifying and pursuing high-impact partnerships, assembling and analyzing relevant data, coordinating and informing future R&D and related activities, and developing new prize proposals. So the thought is that at least each team would have at least one prize proposal. And just to give another little bit more background, the executive lead on this is Assistant Secretary Daniel Simmons, who leads the Office of Energy Efficiency and Renewable Energy. And next slide, please. And I just want to give you guys an idea of what we're looking to accomplish with this webinar series. We're looking to build community surrounding the Water Security Grand Challenge and draw in additional partners and competitors to help meet its goals. To provide a platform to share knowledge, information, and ideas among DOE, its partners, leading innovators, and the public. And finally, to provide a means to gather information on barriers and opportunities to meet Water Security Grand Challenge goals that can inform future prize ideas. So I can't stress that enough. We are here to share information, but we would like your input as well. So with that, I would direct you to the website, and this way you can stay looped in for our future webinars and future announcements. And with that, I'll turn it over to Avi Schultz to discuss goal number 1.
Thanks, Kevin. As Kevin indicated, there are multiple goals in the Water Security Grand Challenge, and the first one is focused on really developing technologies for desalination that can deliver cost-competitive clean water. And as Kevin indicated, this is an interagency effort led by DOE, but certainly involving other federal stakeholders working on desalination technologies like the Bureau of Reclamation and the Department of Defense. And what this effort is really focused on is advancing desalination technologies to expand the utilization of non-traditional sources of water, so sources of water that aren't currently used to provide fresh water. And by doing this, we can really ensure water security in the U.S. and improve the resilience of American infrastructure. Next slide, please. Recently, we announced one of the first efforts as part of this desalination thrust in the Water Security Grand Challenge. And this is a prize focused specifically on solar desalination called the American Made Challenge. And what this is really focused on is developing solar thermal desalination technologies and demonstrating how they can be used for specific markets and applications. What this prize is a series of contests that will be used to take technologies and accelerate technologies through initial concepts, design, development, and demonstration of novel systems that can use solar power to generate fresh water and really use this in novel ways for highly saline waters that are difficult to purify using conventional technologies. This could involve waters like those produced from oil and gas wells, concentrated brines, or some industrial and agriculture wastewaters. Thermal desalination technologies can purify water with very high salt content without dramatically increasing the amount of energy required, unlike conventional desalination technologies like reverse osmosis. The prize structure is really focused on providing a pathway from the initial concept through a multi-stage prize format to develop prototypes and ultimately field test systems that can provide clean, accessible water using solar as the primary energy source. Additionally, the solar desalination prize will seek to connect technology innovators to both potential customers and test facilities to develop fully successful commercialization teams. These teams will be competing to develop concepts that can really compete on a number of important metrics, including the thermal efficiency of the solar desalination process, the amount of water that can be recovered from the brine that's input, being able to operate continuously even with a variable solar input, and of course the solar efficiency of the entire system, and ultimately showing that these technologies can be cost competitive in terms of both the levelized cost of solar thermal heat produced and the levelized cost of water produced. With that, I'd like to introduce the presenter for the next goal, Elena Melchert from the Office of Fossil Energy, who will discuss Goal 2.
Hello.
Eckert. I'm Division Director for Upstream Oil and Gas Research in the Office of Fossil Energy in the Office of Oil and Gas here at the Department of Energy. The goal number 2 focuses on transforming produced water from a waste to a resource. And produced water is that water that is produced with oil and gas during normal operations, and also that water that's produced during the normal operations of uranium mining and extraction. Can I have the next slide, please? About 45% of oil and gas produced water is used within the oil fields, which leaves about 55% available to use outside of the oil and gas sector. The map shows the location of 8 field laboratories within the oil and gas sector that are an important part of our research portfolio. All of these field laboratories are exploring the use of hydraulic fracturing as a stimulation technique to increase oil and gas recovery. Produced water is used in both drilling, completion, stimulation, and workovers, and all of that, the completion and stimulation include hydraulic fracturing, which uses a lot of water at this time, or can use a lot of water. There are hydraulic fracturing techniques that do not use any water. Produced water is also unique to the geologic setting in which it resides. So produced water is not produced water is not produced water is not produced water. The constituents of the water differ as you move across the country from geologic basin to geologic basin, and they differ geologically as you move down the rock column, and they also differ over time in the same well. So it's a big challenge to chase after trying to treat that water for some other use outside of the oil and gas sector. Hence the prize, hence the great challenge, the grand challenge, to transform produced water from a waste to a resource. And water has gotten a lot of attention of late. The Department of Energy's Water Desal Hub was recently announced, and the EPA presented the outcomes of their study that looks at regulations, and the Groundwater Protection Council released a report written from the point of view of state water regulators. And Chevron Technology Ventures, an oil company, announced its prize winners for produced water treatment technologies. And we have Goal 2. We have the Water Securities Grand Challenges Goal 2 that we operate from my office. And then last month, my office announced the selection of 4 new produced water treatment projects. So we're greatly invested in this arena and have been for some time. Next slide, please. There we go. We've been involved in produced water treatment for many years, and over the recent past, we've invested in about 60 projects worth over $100 million. And this research was conducted in partnership with the private sector. This is an oil and gas operations cost of doing business, dealing with that produced water. It comes up with the oil and the gas, and so you can't actually take oil or gas to market without removing that water. And as I said earlier, 45% of that water is used in oil and gas sector operations, leaving that 55% available for other uses. The reason, let's see, where am I here? Can we have the next slide, please? The reason you treat produced water is to remove the constituents that you don't need. And the way you treat produced water is to remove groups of constituents in sequence. Moving from left to right along the top of this slide could be what we call the treatment train, in that first solids might be removed, and then the oil and grease might be removed, and each step as you move to the right is higher and higher cost. Ultimately, the far right, you could have drinking water if you can remove all the constituents. And of course, distillation is a way of doing that, right? But it's probably the most expensive way of doing that. So the blue bars represent various technologies that we've invested in that were shown on the previous slide. And just to show that there are different technologies that can come into various steps in terms of the treatment train. Also, not all waters need all treatment. Some may just need to have the oil and gas associated constituents removed from them. And then once that's removed, perhaps they are much higher quality. So that's why I was saying earlier, water is not water is not water. So in terms of trying to come up with a strategy for transforming produced water from a waste to a resource, depends on where you start and where you need to end up in terms of the quality water that you have to start with, the amount of treatment and cost you need to invest in it, and then the end use for which the water would be made valuable, and then that value perhaps could be monetized. Next slide, please. So Goal 2 is being developed in partnership with the U.S. Geological Survey, USGS, and the EPA, Environmental Protection Agency. The USGS has the largest database of waters in the country, and EPA is the lead regulator for water quality. Together we hope to develop the goal, this Goal 2, in a way that advances all of our needs and uses all of our core strengths. The bottom line is that to transform produced water from a waste to a resource is to perhaps reduce the cost to where it becomes a revenue stream perhaps, and a large volume source of clean water, offsetting the use of fresh water. And to do that would be the grand challenge of connecting supply and demand. So that's sort of the current state of goal number 2. And so now I'd like to introduce the next speaker, who is Roby Lewis on goal 3. Thank you.
Hi, my name is Roby Lewis, and I wanted to talk to you today about the third goal. And you see the words for us, our goal here on the screen. That is to achieve near zero water impact for new thermoelectric power plants and to significantly lower freshwater use intensity within the existing fleet. So go to the next slide. The question is, why are we looking at thermoelectric cooling? As you can see on this slide, this is data collected by the National Energy Technology Laboratory that's showing the national relevance to the thermoelectric problem. So on this chart, you see overlaid projected population growth, as well as with on top of water stress and planned thermoelectric plants of various types. Those are the light purple dots on there, the new builds. So as you see, different areas of the country are experiencing different problems. Some of these cases, the projected increases are in population are driving an increased concentration of new builds, which then creates a higher water stress. Another, this dynamic is actually coupled by already existing water stresses. So the timelines really need to be shortened in those cases. And work in this area also benefits the existing plants already located in water scarce areas. So on the next slide, we talk about, as we look closer at the thermoelectric plants, one quickly realizes that it's the choice of cooling technology that really is impacting water consumption and water use or water withdrawal. Here on the screen, you see 3 different types of cooling. Once through cooling, for people not familiar with that, extracts water directly from a river or a pond, and it cools in through the condenser and then is released back into the river and pond. So this has a high withdrawal rate or a high use rate, as we have on this chart, but a very low consumption rate. The water is returned to the river. On the other hand, in the middle diagram, you see a recirculating cooling tower. In this case, there's less water withdrawn as it's a closed loop cycle, but that water has to be, makeup water has to be fed in there due to evaporation that comes from the cooling tower. So in these cases, there's a higher water consumption that occurs. And then dry cooling is actually uses air to cool instead of the water. So there's a very smaller water use in that. So really, the point of this slide is just to emphasize that the cooling system employed at the plant is often a greater determinant of water usage than the particular generating technology itself, both in terms of water consumption and water withdrawal. So if we go to the next slide, you'll see graphically that once through cooling, which is that second column, they typically withdraw 10 to 100 times more water per unit of electric generation than cooling tower technologies, which is the first column. You'll note that across the bottom, it's hard to read, but there's a variety of generating technologies, electric generating technologies is what, as I referenced on the previous slide. So on the next slide, that's looking at withdrawal, again, once through having a very high withdrawal, 10 to 100 times. On this slide, you see that cooling tower technologies actually consume about, or at least twice as much water as once through cooling. And then in the fourth column, you see the water consumption for dry cooling is actually an order of magnitude less than for recirculating cooling. So depending on whether you're trying to tackle the water consumption or the water withdrawal problem, there's different opportunity spaces. So next slide. So coming out of the workshop the October 25th workshop that Kevin referenced, there's one promising concept that came out, and that's something focused on new cooling technologies. Cooling, as I've mentioned, is the major water draw from within the power sector. And technologies, there are technologies that exist to reduce water in cooling applications, but they typically come with an energy or a cost penalty and haven't been demonstrated at scale, these solutions. So we look at it as an opportunity to build upon recent investments by the DOE programs to help reduce these penalties associated with these new technologies. On the next slide, there's reference to, this is information that's pulled from the Water Security Grand Challenge website, which the link was shown to you earlier and probably will appear at the end as well, I believe. At this, you see these are the programmatic efforts that have led up to our thinking about the prize. So ERE-AMO has had some activities in materials and harsh environments. ARPA-E has had the ARID program. Advanced Research in Dry Cooling is what ARID stands for. FE has had several solicitations, funding opportunity announcements this year. There's actually one open currently on the street now for dry cooling. Nuclear energy has had also a couple of FOAs that have gone out, also has one open on the street now if you're interested in looking at that. And an existing plant water usage and cooling system paper that was written by the Office of Policy. So as we inform our prize definition for our goal, it's most likely that we want to look at these recent activities and figure out what the best opportunity space we will most likely use an RFI to inform our prize definition, and one that would take the form similar to what's on the street now, what's currently on the street from AMO office, which is actually in the next topic area. So with that, I'll introduce our next speaker, John Smeagol.
All right, thank you very much. My name is John Smeagol, and I'm the team lead on the resource recovery goal. I also work for the Advanced Manufacturing Office. The wastewater resource recovery prize competition is an important part of, as I said, the broader goal of doubling resource recovery at municipal wastewater treatment facilities. A central element of this prize is an acknowledgement of a relatively untapped segment of the wastewater treatment universe, specifically small and medium-sized facilities. There's a general recognition that resource recovery activities are existent at larger facilities, but not so much for the smaller or medium-sized ones. In addition, the Envision Prize structure calls for multidisciplinary teams of stakeholders that propose sort of holistic community or watershed-based resource recovery plans. Expected or anticipated teams are likely to be comprised of wastewater treatment facilities, engineering and design firms, technology developers, as well as resource customers, which would include farmers, utilities, and others. These expected teams, the structure of these expected teams sort of recognize the need for effective small and medium-sized water resource recovery solutions to address the entire spectrum of wastewater recovery. That is, from generation to technological solution and ultimately to final consumption of the recovered resources. Question is, why is this particularly relevant? The answer is wastewater treatment is not cheap. Wastewater treatment facilities spend approximately $2 billion a year in electricity and face more than $200 billion in capital expense requirements in order to meet their wastewater treatment, effluent requirements. And these sorts of expenses are stressed to any municipal government, let alone a small or medium-sized one. In addition, anticipated increases in energy costs will only exaggerate these impacts, as will biosolid disposal costs. Despite the situation, there is presented an opportunity, which that is the intent of the prize. Wastewater treatment plants can address some of these challenges by recovering additional resources and turning them into marketable products. Therefore, the revenue streams from these recovered resources can therefore help offset the significant portion of the cost that they have to face. Examples of resources include the energy that can be used on or off-site, sold back to the grid potentially, nutrients such as phosphorus or nitrogen that could be employed as fertilizer in agricultural settings, obviously, and clean water or an increased clean water itself, which could be reused in agricultural, industrial settings, or in potable circumstances. As currently envisioned, the prize will consist of two phases. Phase one includes two major components. The first would be what we're terming at this point sort of a high-level schematic or engineering diagram. It defines sort of the process flow, the major components of the system, opportunities for changes there, and sort of describe in a visual sense the way in which the ideas that are being submitted for the prize competition interact with the existing system to generate these recovered resources. The second major component would be a business plan, which involves a sort of a cost effectiveness discussion as well as a viability discussion, which again gets back to that whole notion of having the full sort of from generation to extraction to ultimate consumption. And that really gets into the notion of viability and what we're terming the business plan. Successful plans will demonstrate how the proposed approach reaches threshold levels, and I'll talk about those a little bit later, of resource recovery. And there will be special emphasis placed on innovation and replicability of solutions when determining those who are selected as winners of this first phase of the prize. Currently, we anticipate around 10 awards for this phase one, about $50K each, and these awards and their descriptions would be employed ideally in sort of a library of solutions setting that could be looked to as resources for various facilities, which again gets back to why we're looking at the high-level schematic and business plan discussions, because folks can refer to this library and compare to their systems and sort of find analogs that might be appropriate for their deployment in their settings. Phase two is sort of a down select of the most promising of those ones selected in phase one, and there'll be a lot more time elapsed. We are still refining the actual time period, but under the phase two, the selected projects would need to submit more detailed and rigorous demonstrations, which would be supported by quantitative analysis and modeling data. Phase two submissions will be aligned with application requirements for existing public financing programs, say for under WIFIA or State Revolving Fund or others that might be available. Again, with always towards a mind or an eye towards ultimate likelihood of implementation. And as I referred to earlier, metrics are going to play a critical role in the evaluation, the threshold, whether it's some sort of recovery rate that we're going to be looking at, or a rate of improvement. Some of these will need to be defined through what I'm going to talk about in just a second, which is, next slide, please. In support of the refinement and definition of the rules and construct and structure of this prize, we issued an RFI, which was announced at WEFTEC on September 23rd. The existing RFI closes on October 23rd. The links for this notice, both on the EER Exchange, which this is the lower one, the Federal Register notice itself, which is the middle one, and then the top one is sort of the DOE sort of press release that accompanied that also has the appropriate link. So any of these three will get you to the details of how you would submit your questions or input on the RFI, and that's really what we're looking at. We're trying to solicit stakeholder input on the overall prize concept, whether or not there are analogs. We're looking at resource recoveries, what sort of state and local policies are effective, what are potential barriers, which stakeholders are critical. We're also looking at how we should design the prize, the actual phases, the incentive levels, whether or not we're using an appropriate cutoff for small and medium sized. And then lastly, we're looking at sort of criteria and metrics and what are the most appropriate ones to use in terms of ultimately will result in a well-structured and effective prize competition. And at this point, I'd like to turn it over to John Carmack, who will discuss goal number 5.
Thanks, John. This is John Carmack. I have the pleasure of presenting Goal 5, develop small modular energy water systems for urban, rural, tribal, national security, and disaster response settings. As you can imagine, that's, with that broad class of potential applications and challenges, it's become really an inspiring goal with many potential beneficial outcomes. We've generated interest and participation from across a number of different organizations from within the Department of Energy, associated with maybe the different types of energy generation technologies, as well as outside the Department of Energy with the U.S. Agency for International Development, and looking at potential applications and uses in developing countries that are typically water stressed and in need of energy resources, as well as in the Department of Homeland Security and the FEMA organization, looking at potential uses and applications in recovery in communities that are affected by disaster and emergencies. We've narrowed down our objective to really specify developing a fuel-agnostic energy water-in-a-box solution that is modular, portable, reliable, and cost-effective across many different energy generation capabilities. We can imagine many different types of energy being used at the small and modular level to be coupled with a variety of water treatment and purification technologies to fit specific applications. We imagine that small modular energy water systems have the potential to serve areas where energy and/or clean water is scarce, expensive, and challenging to obtain. We've looked at use cases in islanded communities, rural areas, and communities affected by disaster. But we believe that innovation is needed to improve the cost effectiveness of these energy and water linked systems, to improve the overall test capability or the overall system capability and fit a range of use cases. We imagine starting with, we've identified 3 general use cases of 1, a response and recovery use, 2, maybe application to water scarce and developing nations or communities, and then also application to remote and island communities that might require longer duration operation and efficiencies. We would like to begin with a multi-technology ideation prize to identify promising concepts and business plans across these use cases, and then hopefully launch that multi-technology ideation prize in fiscal year 2020. We expect that our sample metrics could vary by use case, but we would expect to look at the portability and speed to deploy, possibly the continuous operation capability, coupled with low maintenance and high reliability, as well as the cost effectiveness of these coupled technologies. We're still a little bit out in actually releasing that. We think that we'll have that sometime in the early part of 2020. And with that, I'll turn it over to Melissa Climbara to present the cross-cutting area.
Okay, thank you. So I'm Melissa Climbara. I'm also from the Advanced Manufacturing Office, and I'm here to talk to you today about the Energy Water Desalination Hub. Next slide, thanks. So about 2 weeks ago on September 23rd, the Secretary of Energy announced the selected award for the Energy Water Desalination Hub, which is a $100 million early stage R&D consortia. It's really meant to be sort of like these, like a mini Manhattan project of getting together lead scientists from across industry, university, national labs, nonprofits, to really focus in on developing new technologies for bringing down the energy intensity and costs for desalination technologies. We selected the National Alliance for Water Innovations, which is led by Lawrence Berkeley National Lab, and they have 35 main members with over 180 other participating organizations. And we're also looking for more participants. As Kevin suggested earlier, we're trying to build out this community, and so we really want folks who are interested in joining the hub and being part of this research effort to go to the website I have identified there, nowihub.org, and you can learn about how to become a member. During the first year, some of the key activities that we'll be doing is really building out these roadmaps that you see in that kind of first petal layer of roadmap clusters. And so there's 9 source water roadmaps that we'll be developing with key stakeholders, such as yourselves, to get input on what the research priorities should be for the hub going forward, and then compete those research priorities broadly with anyone that's a member of the hub. We'll also be gathering a lot of data and analysis on what the current costs are. One of the strategic goals of the hub is to achieve pipe parity water. So what we're trying to do is how do you develop non-traditional water sources for these multiple end-use applications, but at the same cost parity as current fresh water. So we're trying to gather a lot of data related to the various sectors identified in the roadmap clusters to baseline current states of technology and set targets related to how we can bring down the cost and energy intensity through different research priorities identified in the stakeholder road mapping over the next year. One of the key visions of NOWI is to kind of what John just talked about is kind of modularity. So a lot of the energy intensity of water is through moving it, transporting water. And so NOWI's vision is for this distributed desalination and water use. So how do you, through process intensification type technologies, how do you get to distributed modular systems so that, you know, using our existing water structure that is centralized, but kind of augmented or supplementing it with these modular systems so that you can almost have like a microgrids of water to keep water local and reuse it locally. And that will take out a lot of the energy intensity and hopefully the cost of water. So the hub is cross-cutting because it's addressing a lot of all 5 of the grand challenge goals. And so we're really excited about the announcement that the Secretary made 2 weeks ago. And if you're looking for more information and want to get involved, please go to the website identified there or contact me directly. Thank you.
All right, great. Thank you, Melissa, and thank you to all of our presenters, Kevin, Jane. We've also listed out the website for the Water Security Grand Challenge, and also Melissa Climbara's contact information is here as well. So we thank you for listening, and we plan to have our next webinar in 2 to 3 weeks, so be on the lookout for the announcement for that and the call-in information. And so with that, we will conclude this webinar and hope to welcome you to the next one later this month. Have a great rest of your day.